I'm Belinda, and I work in the Wilson Brain Imaging Center, and I work on this thing called the parallel transmit. So a bit of background, I'm sure everyone knows this. We have a 7 Tesla Siemens Terra scanner up in Edinburgh. What's special about this scanner is that it's the first FDA-approved 7T scanner, so it can be used for clinical diagnosis purposes. But to a physicist, what's special about this scanner is that it comes with an integrated parallel transmit host. And I'll talk a little bit more about what that is. So before we get to that, let's talk about why we want to image at ultra-high field. Firstly, the higher field means that there's an increase in signal-to-noise ratio. So this can shorten scan time, but more importantly, it greatly improves the resolution of the image. So at 7T, we can obtain sub-millimeter, like 0.4 millimeter isotropic images of the brain. There are also changes in relaxation times, which in this case greatly favors the FMRI bow contrast. So clinicians are always glad of the advantages associated with 7T, but working at such high fields can be challenging from a physics point of view. Firstly, there's an increase in specific absorption rate, or SAR. So this is the amount of energy and heat that's deposited in the subject during a scan. We do not generally like to burn our volunteers, so we like to monitor this quite closely. Lastly, there's a huge increase in magnetic field inhomogeneities. So we get areas of dropouts or like brightening artifacts, and parallel transmit is able to greatly reduce these artifacts. This is one of the reasons why parallel transmit at ultra-high field is such an active area of research. So a quick introduction to PeakX on the Terra. There's both a hardware and software change. So if you've been to our control room, you've realized like 2 computers that look identical. And one's for the single transmit host, and one's the parallel transmit host. We also have 2 coils. Again, they look very similar. The main difference is that you have this extra transmit plug for a parallel transmit coil. However, if we look at how they are connected to the amplifier, we can see that they are quite different. In the single transmit system, all transmit elements are connected to the same amplifier. This means that we can only play the exact same pulse on all transmit elements, and because it's a birdcage design, there's a 45-degree phase shift, but we don't have any control over the pulse shape or the amplitude. Meanwhile, for the parallel transmit, because each of them are connected to a different amplifier, we can control each transmit element independently. So we can play different pulse shapes with different amplitudes and different phase on each transmit element. Because of this, we get more degrees of freedom, and we can better combat the sort of artifacts I've been talking about. So here's an example of a spherical phantom. This looks really bad. You get a bad this is called a central brightening artifact, and with just a simple half design, it gets quite a lot better. So how do we figure out what to play? It's a bit mathematical, so bear with me. In order to calculate the PeakX pulse, we first define our target magnetization, so what we want our images to look like. For most imaging purposes, we want it to be as homogeneous as possible, but we can excite specific spatial locations as well. So this is what our PeakX group does. You do your own logo, and we have for Cambridge. So now we have a target, and we need to figure out what our starting point is. And we do that by obtaining the B0 and B1 maps. Here's a set of in vivo B0 and B1 maps. B1 is a complex quantity, so you have both the magnitude and the phase. And the sensitivity of the coil actually decreases quite dramatically as the distance from it increases. So you get this like bright spots that goes around, and this shows you where each transmit element is. Next, we need to define a transmit k-space trajectory. So this is a version of the block equation. This is the transverse magnetization, and it depends on quite a few things, like the pulse shape, the gradients, the position. And we can simplify this slightly by defining this thing as the transmit k-space. So it's basically taking the integral from point in the pulse to the end of excitation. It's a bit similar to image k-space. Like image k-space, we can plot it out in a 3-dimensional plot. So here are some possible trajectories we can take during excitation. This one, the one with one spoke, that's basically a single GZ gradient, so a slice selective pulse. that will be what the transmit space looks like. We can also do a number of them, and we get this thing called spokes. For 3D excitation, if we don't play any gradients at all, we get a single point in the center of transmit K-space. That's basically a rectangular pulse with no gradients. But we can do many cool trajectories like KT points, spins, spirals, and people have come up with all sorts of weird, wacky ideas. So in order to choose the correct K-space trajectory, we have to decide firstly if we want to do 2D excitation or 3D excitation. In my case, I've chosen a 2D excitation because I'm trying to use it in FMRI, and I chose spokes because that's the most common, that's the easiest. You see 5 spokes here, and each spoke is about 2 milliseconds. So for FMRI, it doesn't make sense to have a 10 millisecond excitation pulse. So I've reduced the number of spokes to 2 spokes. How do we decide where to place the spokes? It's actually quite simple. We take a Fourier transform of the target magnetization, and we just place the spokes on the points with the highest magnitude. And that seems to work quite well. And it saves time, and we don't have to optimize it. So we know this green term now. This is for one transmit element. We have not considered 8 of them. To expand it to 8 transmit elements, what we do is that we sum it across all 8, weighted by the sensitivity profile which we get from the B1 maps. This looks really complicated, but we can simplify it into a matrix notation that looks like this. And that becomes a simple optimization problem. So M is the magnetization. A contains everything we know, so the B1 maps, the B0 maps, the gradients, and B is the pulse. So here's a least square, so it becomes a least square optimization problem. And we usually do it with some sort of regularization parameter so that we have control over where the pulse is deposited and things like that. It also happens that for most imaging purposes, we don't really care about the phase of the image. So what people usually do is to do a magnitude least square optimization. So here's an example of what a spoke's trajectory looks like. You have the Z gradient that moves it in this direction, and you have the XY blips that shifts it in the XY plane. If you did not understand any of the thing I've said over the last 3-4 minutes, don't worry, because this is what it looks like on the scanner. You choose spokes, you click scan. Right now it's acquiring B0 and B1 maps. I've sped it up slightly, but it takes usually sort of 45-50 seconds. And what it does is that it feeds the data to a MATLAB compiler that's running on the scanner, and that calculates the pulse for you. You click OK, and it runs, and you basically have done PeakX. And this is only possible on a Terra where you don't have complicated data transferring steps, you don't need to code, and there's no extra calibration steps. So, on to the FMRI study that I've conducted. I do like to say that this is my first neuroimaging study, so if you do have any suggestions, let me know. We started out by implementing a 2D GRE EPI sequence using spokes and CP mode. So CP mode is where we get a PeakX coil and we make it behave exactly like a single transmit coil. So we say we don't do a proper pulse design, we just make it play the same thing on all channels. We scanned 6 healthy volunteers and we collected data from both resting state and 2 paradigms for each mode. For all acquisitions, we did 30 slices across the temporal lobes and with a resolution of 2 by 2 by 2.3. For the PeakX acquisition, we went one step further. We divided the slab into 5 parts and we had different pulses for each sort of group of 6 slices. Lastly, we obtained the standard MP2H structure sequence and the reverse phase encoding sequences. The 2 paradigms I used, the first one is from Johan. It's a simple functional localizer with 4 kinds of images: faces, objects, scenes, and pattern. It's a one-back task, so participants were instructed to press a button if any of the image repeats. The second paradigm is a semantics association pattern matching task developed by AJ. For the semantics association block, the participants were required to choose which of the 2 images at the bottom is more related to the image at the top in meaning, and for the pattern matching task, which one's identical. So in case you're wondering, that's the Australian map for the koala and the one on the left for that pattern. For resting state data, I've only looked at the TSNR, so I did distortion correction followed by motion correction, and I looked at the TSNR maps. I've also calculated the percentage TSNR change, which is the difference divided by the mean TSNR. Here's a single slide from all 6 participants, and you can see that PTX does actually increase sort of signal in areas in the fusiform and the temporal lobes by quite a bit. If I look across the entire set, this is what I get. So I calculated the percentage TSNR change across 7 RIs in the cortical region. Each X represents 1 participant, and we do see a significant increase over these areas. Overall, there's an average about 10.4% increase in TSNR. Sorry. On to the functional data. Here's the workflow. It's quite a lot of words, I know. But in short, I computed the 2 contrasts. I computed 2 contrasts in the functional localizer paradigm, namely scenes versus faces and scenes versus object, and of course the semantics versus pattern in the second paradigm. For both paradigms, I evaluated the performance of each mode by comparing the percentage change in functional to noise contrast and the number of active voxels. So here's what we found. Overall, we saw an increase in both functional contrast to noise ratio and cluster sizes across all RIs for both paradigms. For the first paradigm, there were quite a lot of literature data, so I could get the coordinates for these regions. But for the second paradigm, it's less commonly used, and I end up using the structural RIs instead, and I'm not sure if that's the right thing. So if anyone has any suggestions about how I should have done this, do let me know. Averaging across all RIs, we saw an increase, a 10% increase in functional contrast to noise ratio, and about a 25% increase in the number of active voxels. So here I've shown you the data from one of the first studies that uses PTX in a task-based FMRI, and so far I would say that the results do look optimistic. So moving a little bit away from FMRI, we also tried some other neuroimaging. This is a 2D turbo spin echo sequence, and we did it with static PTX. So static PTX is sort of the halfway point between dynamic PTX, which is what I've shown you so far, and single transmit. It still requires the PTX hardware, but it doesn't require as much of the optimization software. Instead of those crazy transmit k-space trajectories you've seen just now, it does not modify the gradients during excitation. Instead, it only optimizes the phase and the amplitude of each pulse. On our current version of the scanner software, it does not require any extra modification to the sequence, so it acts exactly like V0 shimming. There's a drop-down box, you select your sort of shim volume, and it just runs. And you can see that there's some sort of signal recovery, especially in the cerebellum area. I know this is not a brain, this is a liver, it's important too. So this is something that we've been working very hard over the last couple of weeks. So we borrowed a coin from Oxford, and we had to perform all sorts of safety tests, and we managed to obtain one of the first set of liver images on the Terra. We did this thing called TIAMO, and it stands for Time Interleaved Acquisition of Modes. What it means is that you acquire 2 images with different shim settings. They're preset. So we did CP+, which is the 45-degree one, and CP++, where the neighboring transmit elements has a phase shift of 90 degrees instead of 45. So it's just 2 arbitrary shim settings. But because of this, the areas of dropouts, like they shift, they do not stay in the same places because the artifacts are different. And by doing a grappa-like reconstruction, we get the image at the bottom. And you can see there are a lot less areas of dropouts, and it's a lot more homogeneous. Lastly, remember how 70 can create a problem with SAL. So here are some preliminary results from me trying to do inversion pulses with PTX. Traditionally, we use adiabatic pulses for inversion, and they work perfectly. So if you look at this, inversion efficiency is almost perfect. But the problem is that they're extremely SAL intensive, so you need very long TRs, you can't use them very often. So what we tried to do is to design a PTX spiral pulse that does 3D inversion instead of using adiabatic pulses. It's still very much work in progress, so you can see it doesn't look as good, but I do like to point out I'm only using about 5% of the power, and I'm about 40% shorter in pulse length. When we applied it to a segmented API T1 mapping sequence, these are the images we get, and these are the T1 values we are getting, and they look very comparable to each other. So we're actually quite optimistic about this, and we're looking at applying high flip angle pulses with PeakX into other sequences like turbo spin echo or T1 mapping. So in conclusion, spokes pulses improve the quality, especially in the temporal lobes for FMRI acquisitions. Perhaps a more simple method would only involve B1 trimming, but that also improves the overall homogeneity of the image. So it's easy to use, and now we have a simple workflow that is clinically feasible. So anyone can use it. It takes a while to set up. You might need a bit of help. We might need to optimize it a bit, but once it's set up, anyone can run it. It doesn't require coding. It doesn't require an extra computer. Moving forward, we are obviously looking at implementing PeakX in a variety of sequences, depending on what people want. So far we're looking at the turbo spin echo sequences because they don't really work very well at 70. We're also trying to understand more of the Siemens framework because they take care of the power calculations, like the SAR calculations. And right now, they are overestimating SAR by quite a bit, so we can't play out as much power as we should. Lastly, as we move to larger flip angles, it becomes an optimization problem because the block equation is no longer linear. And obviously, we are working on that, and we are looking for people who are interested in collaborating. So yeah, thank you for listening, and thank you to all these people who have helped me.